Hello, everybody. I am Nicolas. I'm currently employed at JP Morgan, which shoots a state of affairs that should last right until the moment where the return to the office mandate kicks in, which should be any day now. But enough about my troubles. Why are we here today? I'm here because I want to teach you how to write a general-purpose programming language. And I hope you're here because you want to learn that, otherwise things might get a little awkward. But I think you should want to learn that. I think you should want to learn it because first, it's going to give you a new perspective, it's going to give you new insights on a tool you presumably use most of the day, most days. I also think you should want to learn that because, if you can do the relatively hard task of writing a general-purpose programming language, then you can certainly do the comparatively simpler one of writing a domain-specific one, which can be an absolute game changer when you have to maintain software whose domain experts are non-technical, because it will allow them to write their somewhat esoteric knowledge directly to the computer without having to go through you as a somewhat dubious translator, and of course allowing you to blame them when things go wrong. And I think you should want to learn this from me because I've done this a few times. Now, I'm not going to pretend I've done a good job of it. I've done a terrible job of it. But I enjoyed the experience so much that I decided to learn how one should go about it. Now, most people would tend to do that the other way around. They would learn how to do the thing, and then they would do the thing. Not me. And in hindsight, this may not have been the right course of action to take, because there's a lot of traps. And I fell into every single one of them, plus a couple nobody even knew about. And there is my real talent. I fall into traps, and I leave to tell the tale, and then I can show you and tell you how to avoid the traps in the first place, so you never even have to worry about them. Okay, so now we know what we're going to talk about, why we should talk about it, and who's going to do the talking. I have to come clean. I doubt I'm going to be able to show you how to do an entire programming language. I do have the slides. I only have half an hour. So I'm going to show you as much of it as I can. But my point is not to show you the entire thing. What I'm trying to do here is to give you the tools so that you can continue on that journey yourself once we're done here. And I hope that I'm going to motivate you to do so because it's really fun and exciting. Okay, now, preamble out of the way. What is a programming language? And the way I like to think about it is, a programming language is a set of terms and the rules to combine them together to convey precise and clear instructions to a computer. These instructions are usually found in the shape of text, which we traditionally call source code, or code for short. And we'll send that code to specialized software to do stuff with. For example, you could take the code and turn it into equivalent code that just looks a bit nicer, and we'd call that a code formatter. You could take the code and produce equivalent code, semantically equivalent code that is faster, and that would be an optimizer. You could take the code, turn into semantically equivalent code into a different language, and that would be a compiler. Or you could take the code, run it, and produce the result of the computation, and that would be an interpreter, which is mostly what we're going to concern ourselves with today. Now, I have been careful to present all these things as functions. You go from code to something. And when you're working with functions, it is important to get your domain and codomains right. Here, the domain is source code. We are going to have to think about how to represent source code. And you may think, right, he did say source code was text, and text is traditionally encoded as strings. So why do we not use strings to represent source code? If you know anything about me and about my work, I tend to be a bit of a snob when it comes to types. So string is just not going to cut it, because there's infinitely many more strings that represent illegal code than strings that represent code. We need to do something better. Of course, text is still going to be part of the equation. It is still the best way we have as human beings of interacting with source code. So text is going to be here, but I'm going to pretend that we have a function that goes from the code, from the source code, from the text, from the string, to the representation we're going to come up with. That function is called a parser, and parsing is very fun. It's very fun and it's a very exciting field, but it would take me about 7 hours to cover the field. So I'm not going to do that. I think I have about half an hour, maybe a bit more if I'm nice. Yeah, half an hour. Yeah, if there's a coffee break afterward, that works. Anyway, where was I before I started messing with her? Half an hour, yeah. So I'm not going to talk about parsing. I'm just going to pretend that it's been done. And now we're going to talk about how to represent the actual source code. The way I like to go about that is to think about the simplest program I can represent. And that would be a number. It's not the most exciting of programs, but it is a program. But I did say a programming language are the terms of the language and the rules we have to combine them together. And if you want to combine them together, you need at least two things. So let's add a way of combining two numbers. Let's add addition. And addition, now that we have numbers in addition, we know that our language has at least two terms. It's either a number or an addition of numbers. And whenever you have one thing that is either a thing or another, you want to think sum types. I'm going to call our sum type expr. It is possible that during the talk I start calling it expr, because as Noel said in an introduction email to a potential employer, I am French, but don't hold that against me, which made a great first impression. So I will sometimes pronounce it the wrong way. Whenever you hear expr, it means expr, and you should pretend that I said that instead. So expr is composed of two possible variants, numbers, which hold a number, and the addition, which has a left-hand side operand and a right-hand side operand. And do you mind if I just take a few minutes to try and duplicate my screen here, because I'm going to hurt my neck trying to look up here. So let me up, and that's going to go here, up. This is not working at all. Oh, and I don't even know what that was any longer. Okay, well, that's not working, so I'm just going to hurt my neck, I guess. Okay, so addition. Now that we have the addition, we have the simplest possible representation of a program that we may want. And we can think about interpreting it now. As I said, we were going to be talking about interpretation. But before we write any code, I'm going to start introducing a formal notation to reason about these things, because right now it's not really necessary. We're working with something simple enough that we can just write the code and get working. But as we introduce more terms in our language, it's going to get more complicated. And I want to have a tool to reason about it without having to worry about the details. So right now, we're going to do that while it's still easy. This formal notation is going to look like that. We have num. Whenever we encounter the term num, which contains value, so that's going to be interpreted to, well, the value that we have inside of it, right? That's pretty straightforward. And that's what that downwards arrow means. It means interprets as. When we encounter add, things get a little more complicated. Not that much, but a little, because what do you want to interpret that as? Well, you're going to want to add the left-hand side and right-hand side, won't you? But the problem is these things are not numbers. You can't actually add them together. They're expressions, right? So how do we turn an expression into a number? Well, we interpret it. We're going to say if the left-hand side interprets to some v1 and the right-hand side interprets to some v2, then anything below that horizontal line is going to hold. Everything above is called the antecedents or the premises, and everything below is a consequence. If what we have above works, then what we have below works. And then we know that interpreting addition is going to be adding v1 plus v2, which gives us our interpreter, which takes an expr and returns what we've seen, right? Addition returns a number, number return a number, so that's going to return a number. And since we're working with a sum type, we don't have much of a choice. We have to do a pattern match. So we're going to do a pattern match. We have two variants. The first one being numbers, and we have our semantics here that tells exactly what to do with it. We just return value. In addition is a bit more convoluted, so I'm going to introduce a helper function, add. And add goes like that. The first number must be interpreted to v1, the second to v2, and then we return the addition of both of them. And that is simple enough, isn't it? So now let's try it. So he's saying that we are going to add num1 and num2. And of course, that is going to interpret to 3 exactly as we want it. Now, what we just invented, expr, here, that's such a common structure that it has a name. It's called an abstract syntax tree, or AST for short. And you should be using that We will be using that a lot, and it's a great thing to know about. It's got two sub-sentences in that name, abstract syntax and syntax tree. So let's unravel those. Why do we call that abstract syntax? Well, if you look up there, 1 plus 2, it is exactly the same expression as that one, isn't it? Or even that one. We are abstracting over the noise that humans like. White space to make it look nicer, parentheses to disambiguate it. It's useful for humans, it's useful for us. But once we have it in memory, we couldn't care less about this. We just want to interpret it. So we are abstracting over the noisy details that humans enjoy. We don't need them. So that would be the abstract syntax. And the tree bit, the syntax tree bit is, well, this really is a tree, isn't it, if you think about it the right way. The operator is going to be the root of your tree, and the operands are going to be the leaves, and you get a tree. You may argue that is not much of a tree, though. It's got a depth of 1, cannot possibly grow. That's really more of a bonsai than a tree. But that is actually a symptom of a problem in our design. Because what if what we wanted to do was, say, not add it to 2, but 2 plus 3? We can't do that. Our AST doesn't support that because we said addition only worked on numbers. And that was a mistake. Addition should work on nested expressions so that we can have a tree that grows as much as we want it to grow. And that is a proper tree, and that is how expression should work. Of course, we've changed the AST, so we need to fix the interpreter a little. Add needs to change a little because it works on expos, but the lovely bit is interpret takes expos, so that doesn't change. That doesn't change either. And we can now fix our example to 2 plus 3 and get what we expected. So that was our first step. And what we should remember of what we've seen so far is this. First, source code is represented as a recursive sum type. Expo is a sum type. It is defined in terms of itself, so it's recursive. And that is traditionally called an AST. And interpretation is done through a simple pattern match. So we have a language now. Well, we have the premises of a language. It's more of a glorified calculator at this point. We could add more operations, multiplication, subtraction, all these things. You've seen how to do addition. It's the same thing. I'm not going to waste your time with that. But we do need to be able to express more complicated computations. For example, computations in which there's a choice to be made, in which you might want to take a decision or another. And this is usually encoded in the language that you know with an if statement. Well, an if statement has a predicate, and if that predicate evaluates to true, then you're going to evaluate the onTrue branch. And if it doesn't evaluate to true, you're going to evaluate the onFalse branch. And that's really all there is to an if statement. We don't need to look any deeper than that, so we can go straight away to writing the formal semantics, which I might every once in a while call operational semantics, because that's their actual proper name. So cond, we need a new term, cond, which has a predicate, an untrue branch, and an all-false branch. And we want to evaluate it to, well, we have a problem here, right? What does predicate evaluate to? Because we have 2 branches. If it's true, we do one thing. If it's false, we do one thing. Then we don't appear to have syntax for that yet. What we do, nothing is saying that we can't have multiple rules for a given term, right? So now we have a rule if the predicate is true, and a rule if the predicate is false. And they're really easy to write. If the predicate evaluates to true, then we evaluate the untrue branch and return that. If the predicates evaluate to false, then we evaluate the onFalse branch and return that. That is straightforward, and we can implement it straight away. How would we implement it? Well, the first thing we do is we need to add a new term, cond, which has a predicate, an onTrue branch, and an onFalse branch. And now that we can represent conditionals, we are going to need to interpret it. Of course, I'm going to move that to its own function, because it's a bit messy. And if we follow our formal semantics, this is saying, if the predicate interprets to true, then we do the onTrue branch. Otherwise, we do the onFalse branch. And of course, that doesn't work at all, because interpret returns an integer. And Scala, being one of the same languages, refuses to take integers in where it expects booleans. We could fix that quite easily. We could do that. That is called truthiness. It is an abomination under God. You should never implement that in your languages. I absolutely hate the notion. The way it works is, you sort of pretend any value looks more like a true than a false. It's more truthy than falsy. And it works. It really does work. It's just, it's a convention, and not all languages will follow the same convention. I remember years ago, I was working in I think it was Delphi, this old programming language, and I wasted, I think, 1 week because I assumed that 1 would be truthy and 0 would be falsy, but they swapped the interpretation. Right, it took me a week to figure that out. So that may be a little slow of me, but still, I wasted a lot of time on that, and as a result, I absolutely hate truthiness. Lots of languages implement it, good for them. I'm not going to teach you that. So we're not going to do that because we have some self-respect. What we're going to do instead is the correct thing, which is to say, well, interpret is not just going to return integers. It's going to return integers or booleans. Again, one thing or another. There's a pattern here, isn't there? We've seen that before. When we have to represent one thing or another, we want a sum type, which I'm creatively going to call value. Value is either a number or a boolean. Simple enough. And now interpret needs to return a value. And that's going to force us to revisit everything we've written so far. We're going to do that quickly. Numbers don't evaluate to value any longer, but to a value.num that wraps that value. Addition, well, addition gets a little tricky, because now that we have 2 different types, we don't want the operands to be any v1 or v2. We want them to be numbers. And this is interesting, because what happens if they're booleans? Well, we don't have a rule for the boolean case. So whenever we go through our rules, if none of them match what we have, that is a runtime tap error. And this needs to be wrapped in a number as well, of course, because it is a number. So we are going to have to change our whole code to respect that constraint, which gives us a bit of a mess. But what this is saying is the left-hand side may be a value, the right-hand side must be a value, and if that holds, then we just add them. Otherwise, we have a type error. And now we can do cond. And cond is going to look quite a bit nicer now, though, because, well, we want the predicate to be a Boolean. That makes sense. Predicate is a Boolean. That's the entire point of this. And well, we don't care about the values, the return values. They could be any type, but we don't really care which one. We don't have any constraint on that, so we're not going to touch them. And we're just going, and return the value, of course. And we're going to rewrite this code to say, well, if the predicate is a Boolean that happens to be true, then we evaluate the untrue branch. Otherwise, if it's false, then we evaluate the unfalse branch. And otherwise, we have a type error because we don't have a rule for that case. So we are going to want to test it, but we're not going to be able to just yet. We don't have that. We know how to have Boolean values, but we don't know how to produce them. We know how to handle them, but not to produce them. So we're going to need to introduce a new term to our language, which is going to be a literal Boolean. That's exactly the same thing as num, so we're going to go quite quickly. Boolean has a value, wraps a value, and when we encounter it, it evaluates, it interprets to a value.bool. We need a new term in our AST, which just wraps the value, and the interpreter just writes itself, doesn't it? Okay, so we have conditionals. We can write our thing that says, if true, then 1, else false, else 2, and that interprets to 1, exactly as we wanted. So far, so good. What we've learned that conditionals are straightforward to support. We've learned that they require us to support multiple types of values, and that we should never allow people to implement truthiness. Please don't. We are getting somewhere. We're starting to have a more powerful language. We are starting to have a language that can express more complicated computations. And since we're starting to have complicated computations, we might want to name sub-computations in order to reuse a result. We're going to want to name things, which you might think of, we're going to do variables. I'm very carefully not going to be using the term variables or the keyword var or the keyword val, because these seem to imply mutability. I don't think mutability is a bad thing, but I also think it's super complex, extremely complicated, and I want to introduce it if we need it. And we don't so far. So I'm not going to use var or val keywords. I'm going to use let, which is a very good keyword that I wish more languages used. And you're probably quite comfortable with what this evaluates to, right? You say x is 1. You dereference x. That's probably going to evaluate to 1. That would make sense. What about that one, though? That one should make you a little more uncomfortable, shouldn't it? I can't actually tell you what it's going to evaluate to. That depends on the semantics of your language. It could evaluate to 1. It could evaluate to undefined. It could evaluate to null. It could throw an exception, or it could just refuse to run if you have the same compiler. The point here is not to decide how that's going to run. The point is this should make you realize there should be a notion of scope. there should be a subset of your software, of your code, in which a binding is valid and and the rest of it is not valid in. So we're going to add this notion of scope to the syntax as just defined with the in keyword. This is saying x is equal to 1 in the body of the late statement, and the body is x plus 1. Okay, so how does that work? Well, we say, well, we have encountered x equal to 1, so we're going to store that knowledge up there, which I'm going to call the environment. And in the body, well, when we encounter x, we replace it with its value, 1, and then we just reduce, get free, and when we have fully reduced the body of a late statement, then we replace the entire statement with a result, with whatever stored in the body. And that is the general idea of resolving bindings. There are a couple of tricks here, and of course I fell right into them. The first one is, what should we put in the environment here? Should we put 1 plus 2, or should we put 3? Both approaches are valid. One is called eager evaluation. If you enter an expression, you interpret it and you store that in the environment. Another one is called lazy evaluation, in which you wait until you absolutely have to before running a computation, so you put the entire computation in the environment, and later you resolve it. There is no right choice here. And you would argue, does it really matter? Because the result is going to be the same anyway. And yes, it will be the same in a pure language, but it might not run as fast in one situation or the other. Here, for example, if we were to do lazy evaluation, so we don't compute x, we just know x is going to be the result of evaluating that expression later. Well, here the statement says if true, then 1. So we're just always going to go for 1. We're never going to interpret x. So having computed it would have been a waste of time. This might seem to imply, well, we should always do lazy evaluation then, but sometimes it's actually going to be slower. Imagine you're doing x plus x, right? And in that case, you're going to end up with 1 plus 2 plus 1 plus 2, which means you're going to run the computation twice instead of just a 1. So there's no good choice. We're going to do eager evaluation, not because it's the best way, but because it's the one I'm the most comfortable with. I'm not trying to imply lazy evaluation is bad, it's less intuitive for me, so I prefer to go with what I'm comfortable with. So eager evaluation it is. Eager evaluation, so we are going to interpret the value before we move it in the environment. Now, this, you should be comfortable with this. This clearly tells us x is 1, so we're doing 1 plus, well, x is 2 now, so we're doing 1 plus 2, and that should be 3. That's correct. What about if I flip the arguments, the operands? Well, addition is commutative, isn't it? So that should not change anything. Well, let's run through it. We're saying that x is equal to 1, so we're binding x to 1. We're storing that in the environment. And x is going to be equal to 1 in that bit of code. And then we encounter x is equal to 2. And what we could do here, the intuitive thing to do, is to say, well, x is now 2. And so this is 2. We replace the entire let statement with its body, and we're doing 2 plus 2, which is 4, famously not 3. Problem. Addition is no longer commutative in our program. That is not a good thing to have. Now, what I've just shown you, a lot of languages are actually implemented like that. This is called dynamic scoping. And I think it's pretty much universally considered a bad idea nowadays, but every once in a while a new language is going to come up and say, I'm going to do that, because that's the right thing to do. I think Python had that for a while, and if anybody lived through the transition, it was, what a fun time it was, wasn't it? So now what we're going to do is lexical scoping. In lexical scoping, or static scoping, we merely have to look at the code to know what the value, what value is bound to a name. Here's how it works. We're going to go here, and instead of, sorry, I went too fast. And instead of overwriting x, we're going to do something entirely different, which is called shadow x. We're going to push a new value onto our environment and say, well, in that body, in that statement, x is equal to 2. Then we run through it, we see that x is equal to 2, and once we replace the body of the late statement, we also pop off that value from the stack, and now we have x is equal to 1. And we have 2 plus 1, which is 3, what we wanted. Now, obviously, I've been using pushing something on the environment, popping something off of the environment. I've been using stack terms. That's not a coincidence at all. The environment clearly can be represented as a stack, which is what we're going to do. Right, so we've seen the traps that we had here. We've seen that, we've seen everything, so we can formalize them in our formal semantics. We can say that let is a new term that has a name, a value, a body, And when we want to interpret it, well, we have to interpret the value, v1, and then we want to interpret the body, but we said we want to interpret the body in an environment in which name was bound to v1, and we don't have a notional environment yet. So we're going to integrate that. We're going to say this, which reads, in environment E, value interprets to v1. And so we can say body is going to interpret to v2 in some environment. And as I just said, that's going to be in the environment in which name is bound to v1. And that syntax up there means E, duplicated, not modified, importantly, in which name is bound to v1. And that tells us that the entire let statement evaluates to v2. So I like how this shows how to solve the traps we've encountered. This is telling us, well, we're doing eager evaluation, because the first thing we do is we evaluate v1 before putting it in the environment. And then we put it in the environment. And this is also telling us we are doing lexical scoping because we are not modifying the environment. We are creating a new one in which the name is bound to the value, but E modified that way is not used anywhere else. Now we can write that. We're going to need formal semantics for, of course, when we encounter a variable and how to look it up. Well, that's pretty easy. Ref has a name, and it interprets to whatever the environment says it has, like this. We have the formal semantics. We're going to need to update our AST, expr, to contain the let term that has a name and a value and a body, and ref has a name, and of course the two names must match in order for that to work. Interpretation, oh, of course, we do need to implement the environment. That is important. So the environment, well, that's, we just said, it's got to be a stack of something. And in Scala, a stack is really a list. So it's going to be a list of bindings, where a binding is a product of a name and a value. And we're going to need a lookup function, which, given a name, finds the first entry that maps to that name, returns a value, or fails otherwise. And we're going to need to be able to bind a new name. That's create a new binding, push it on top of the stack, and return a new environment with that binding. And because we're polite, we're also going to create a way to create empty environments. Right. We need to update interpret. We have to pass the environment everywhere now that we have a notion of environment. I'm not going to show you all the details of how to update all the functions we already have, because that would be a waste of your time. And I have another, oh, dear God. Okay, let is going to move to its own function. We interpret the value, interpret the body in the right environment, and ultimately we get v2, and that's what it interprets to. It's fairly easy, isn't it? There was a lot of thought to produce this simple code. Ref is very easy. We just look it up in the environment and we're done. And now we can try this entire thing. It evaluates to 3. Now this thing, if you remember, evaluated to 4 when we had gotten scoping wrong. So we have apparently gotten scoping right. And what we've learned here is that local bindings have a scope that can be analyzed statically. Very important, the static part. They can be shadowed, but not overwritten. And their interpretation requires an environment which we have just implemented. Now this is telling me that I have 1 minute and a half. I can 3 more? 4? 3.5. Okay, because I could show you functions quickly. I can refer functions. I'm not going to do recursive functions, which are fun, but I'm definitely going to have the time. I'm going to try to do that quickly. And then I'm probably going to be carried off stage and shot in the back. Reusing code, right? We know how to name variables. We know how to name values. This is great. It's not perfect because we also might want to name not the result of computations, but computations themselves. This is, for example, a little frustrating because what we're doing here, we're saying, give me an x, any x whatsoever. Whatever x you have, I'm going to add 2 to it. That is, only if x is equal to 1, however. That works, but it seems like a waste. We could do something like that instead. Here's a function that maps x to 2, and then we apply it to 1. But you could pass any number to it, right? So that would be a much more powerful computation, and the way we would interpret that is by going, right, so that's the function we're going to apply to that number, and the way that works is we are going to say that x is equal to 1 and replace the application with the body of the function. So there's a bit of a switcheroo here. We do this thing, and then x is 1, so 1 plus 2 is 3, and we get what we wanted. Great. Now, Some of you are probably going to be a little upset with that because the function I showed didn't have a name, and we really love naming our things. Functions need to have descriptive names. You need to be able to understand what the function does just by looking at it, which is why we often call them F or J, and sometimes H when we're feeling a little frisky. So we can't do that. We have let, right? We have learned how to name things. We could say that this function has a name F in that body, right? We get to name it F. Now that has consequences, however, because we did say that let are used to bind names to values, or values to names. I'm never sure how that verb works. But here we're binding the name F to a function. So functions must be value. We have just decided that we were doing a functional programming language in the original correct definition of a functional programming language, which is functions are values, no monads involved. Which means we need functions to be values, so we need a new value, fun, which has a parameter and a body. That's not all we need. There's a trick here. Look at that. You should be confident that this tells us y is 1, so this is really x plus 1, and applying that to 3 should yield 4. But if we run through it, I'm going to go quickly because she's staring daggers now. Y is equal to 1, f is mapped to that function, y is not mapped to 2, we're applying f to 3, we do the switcheroo thing, x is 3, and y is 2, and we get 5 when we wanted to get 4. The problem is here, y is 1, so here y should be 1, and it should not be overwritten by that binding. We have brought dynamic scoping back in the fold. That's a mistake. What we want really is to evaluate the function in the environment in which it was defined. So we need to modify fun to capture its environment, to, one might say, close over its environment. I could show you the formal semantics. I could show you all of that. That would be interesting, but I don't think I'd survive the experience. So I wanted to show you.
Do you want him to continue? Okay, go on.
That was very kind of you. Thank you. Right, let's do the formal semantics. We need a new term, fun. Fun has a parameter, a body, and it produces a function that has a parameter, a body, and the environment. That is the key thing that you have to remember about functions. Application is a little more funky. We have a function, we have an argument, and we really hope the function is going to be a function, because if it's not, we have a problem. And it captures the environment, which I've called E prime here. The argument evaluates to v1, and then we have to evaluate the body in the environment in which the function was defined, not in the environment in which it was applied, and that is key. It's also incorrect. We need to bind parameter to v1. Right, we need E prime in which parameter has been bound to v1. And that's it. That's function. That gives us v2, and that's what we wanted. Implementation is straightforward, and we're going to go quickly. We need a new term, fun, which has a parameter and a body. And we need application of function, which has something that we hope is a function and an argument. Parameter, argument. Parameter is a name, argument is a value. So parameter is a binding, and argument is what you bind the name to. Well, function is just creating a function. It's a function literal. We just create a value.fun. And interpretation of ref apply, is going to be moved to its own function, where if fun is a function, then we interpret its argument, interpret the body in the right environment, and that's our result. And if fun wasn't a function, then we have a type error. We can test that. I'm not writing the entire AST because it's starting to get quite noisy, but believe me, that's the right AST, and we get 4 exactly like we wanted if we had implemented scoping properly. Oh yeah, and I just want to quickly show we have support for non-just unary functions. Unary functions are a function that take a single argument, but if you think, there's a lot of functions that take more than one argument, addition famously. If you think about it, we already support that if you think about it the right way, because you could think about function as a function that takes the left-hand side and returns a function that takes the right-hand side and returns, well, the addition of the left-hand side and right-hand side. And we don't even have to add anything to the syntax. That's all there is to it. We have support for any arity, quite unlike Scalar, for example, which I think is still limited to a number of parameters. Expr, yeah, I'm not going to do that. That's way too much of it, but it's interprets to free, which is nice. What we've learned about functions, their values, they close over the environment, very important. And yes, unary functions are entirely sufficient. Where's my mouse? Yes. You see, I have this trick when I have this trick where I lose my mouse, apparently. Okay, so in theory, I should be able to click key takeaways to go to the conclusion slide and skip over the rest of the presentation, but I can't find my mouse cursor, so that's going to be the last slide. What we've learned then is to implement a programming language, you need an AST, an abstract syntax tree. And honestly, if you remember that and nothing else, I've done my job and I'm happy. But we've also learned that in order to reason about your AST and about your language, formal semantics are extremely useful, which is actually quite timely because I've seen a talk by Leslie Lampert, I think last week. I don't know if anybody has seen it. It's called What's the Difference Between a Coder and a Programmer, in which she explains how to think about things using abstract syntax before writing the code, and that really fed into my whole thing here, so I felt I should mention it because Leslie Lampert agrees with me. This is nice. And I wish I could show you more. I wish I could show you recursive functions. I wish I could show you types. I wish I could show you static typing, type inference, typed ASTs, typing the environment in the AST. All of that is really fun. If that sounds interesting to you, I'm currently writing articles about that. I have a link on the last slide, which I can't get to. So while I'm talking, I'm just going to do that. There was a little bit more to this talk than I just gave. But what was I saying? Ah, that was it. Yes. Yeah, there we go. That would be the link to the articles if you're interested. And in the meantime, I would like to offer you to give you the opportunity to ask questions, but I doubt that's going to happen.
First of all, I have a question. Which part of 25 plus 5 you did not understand?
I have a bug in my program. Thank you.